Hello everyone, in this work we propose a generative semantic segmentation method. Most existing semantic segmentation methods belongs to the discriminative learning paradigm, where methods learn discriminative features between different categories and predict masks for n classes. In Construct, we propose a generative semantic segmentation approach that views semantic segmentation as an image generation problem and incorporates a latent space to construct a fully generative framework. First, let's take a closer look at what semantic segmentation is. Semantic segmentation involves classification for every pixel in an image, addressing the question of what objects are in the image and where they are. Traditional discriminative model learn the category boundary and predicts a number of masks. This kind of method has evolved over years but consistently remains within the discriminative framework. However, we consider the possibility of utilizing the popular generative frameworks to model the problem of semantic segmentation, and the final result presents that is a great avenue for exploration. To build a generative framework, we start by assigning a special color to each category, representing the n-class masks as a unique image. Since the color and the category are one-to-one, it's easy to define the function that maps from the category mask to the maskage that is a special image, and conversely, we can also obtain the category mask by calculating the similarity between the color of the maskage and the color of the category. Based on the novel concept of maskage, we can redefine the traditional pixel classification task as an image generation task. As shown in Figure B, our generative framework takes an image as an input and generates a new image as output, that is maskage. Now, let's explore how we train and infer our generative framework for semantic segmentation. Firstly, we define a general optimization objective for semantic segmentation, which is maximize the probability of the target class C given the input image X. Our GSS also introduces a latent variable Z as the bridge between the image and the maskage. In this context, we can obtain a lower bounds for it based on the evident lower bounds formula, that is the elbow. Explaining the elbow formula reviews two terms. Each of them has some condition probability which can be built as a module in our framework. In GSS, the first conditional probability indicated by the green underline corresponded to the module generated the maskage under the latent variable Z. We name this module as the maskage decoder. The second conditional probability indicated by the orange underline involves generating the latent variable Z based on the maskage. We refer to this module as the maskage encoder. The third conditional probability indicated by the blue underline generates the latent variable Z based on the image input. We model this module as the image encoder. The training process of GSS consists two stages. The first stage involved obtaining a well-performing maskage encoder and decoder. The second stage is to train an image encoder which encodes the image into the latent space. In the first stage, our objective is to obtain a maskage encoder and a decoder. Since we have already assigned the colors to each category and obtained the maskage, which is a special RGB image, we can bypass the step of training a dedicated autoencoder for maskage. Instead, we can use a pre-trained image autoencoder to accomplish this task. The design proves to be highly effective. During the stage 2, we aim to train an image encoder to encode the information of an image into a latent space Z, while aligning it with the corresponding latent variable of the mask gauge. This way, when Z is provided as an input to the mask gauge decoder, it can be accurately decoded and generates the corresponding mask gauge from the input image. During the inference, we input the image into the image encoder, obtain the latent variable Z. Next, we use the mask gauge decoder to decode the latent variable Z to generate the corresponding mask gauge. Finally, we utilize a map from the mask gauge to the category mask to obtain the final segmentation result. For the experimental result, we achieved competitive MLU scores on CSCAP and ADE20K. We have also achieved new state-of-art performance on the cross-domain dataset MSEG. Here are some qualitative experimental results on CSCAP and ADE20K datasets. In conclusion, in this paper, we have presents a generative semantic segmentation approach. We reformulate segmentation as an image generation task. Our formulation is distinctive to discriminative learning-based alternatives. Thank you.